In the previous video in this series, linked in the description box below, we discussed how a rate law for any given reaction was the linear fit of experimental data, and every rate law was identical, where the rate is equal to K times reactants raised to some order. In this video, you will see how this can be used to get theoretical data, specifically the mechanism of a reaction. A mechanism answers the question exactly how does a reaction occur. If you think about a reaction, it's a bunch of molecules colliding. In the real world, multiple things will not collide with each other simultaneously. If you think of any accident on the highway where several cars get involved, all those cars do not hit each other at once. What always happens is car A hits car B, which gets pushed into car C, which gets pushed into car D, and so on and so forth. The same occurs with a chemical reaction. A reaction is a string of bimolecular collisions, meaning molecule A collides with molecule B. Because of this, each fundamental step is first order. If the only thing that's occurring is A hitting B, the only two things that matter are how much A you have and how much B you have. Thirdly, the rate of the slow step in the mechanism has to equal the experimental rate. Essentially, the reaction can't go faster than its slowest step. And finally, the mechanism has to make sense. You can divide the reaction up into as many steps as you want, but when you add those steps back together, you better get back to the original reaction. The mechanism has to obey Hess's law. These last 2 points constitute proof of whether a mechanism is possible or not. The rate of the slow step has to equal the experimental rate, and all of the fundamental steps have to obey Hess's law. How this works in practice can be seen with a couple of examples. Take the reaction which we've seen before. NO2 plus CO goes to NO plus CO2. Experimentally, this reaction has been found to be second order in NO2, but totally independent of the amount of other reactant, carbon monoxide. Since it's obvious that you need carbon monoxide for this reaction to occur, the question is, why doesn't the rate depend upon it? So the following mechanism is proposed. A two-step mechanism where at first NO2 reacts with NO2 to make NO plus NO3. Since NO3 is unstable, this step is relatively slow. Also, since NO3 is unstable, if it does form, it will immediately react with carbon monoxide to give you NO2 and carbon dioxide. So, is this possible? 2 things to check. First of all, does it obey Hess's law? When I add the reactions up, I see that NO3 shows up on both the left hand and the right hand side of the arrow, so it cancels. As does one of the NO2s on each side is going to cancel, leaving me with NO2 plus CO going to NO plus CO2. In other words, the reaction matches the original reaction. Hess's law is satisfied. The second step, I look at the rate of the slow step. As mentioned, each individual step is first order, so it only depends upon the concentration of each individual reactant. Also, all rate laws are the same. So the slow step is going to be equal to a K for the slow step times the concentration of the first reactant, NO2, times the concentration of the second reactant, NO2, or essentially the slow step is equal to some constant times NO2 squared. So it's equal to the experimental rate law. Therefore, this mechanism has been proved to be possible. A second reaction. H2 plus 2NO goes to 2H2O plus N2. It's found to be second order in NO, but only first order in hydrogen. A more complex mechanism is proposed for this reaction. The first step is a rapid equilibrium, where NO and NO form a very unstable adduct N2O2. Some of it falls back apart in the equilibrium. Whatever survives slowly will react with hydrogen to give me one water and an equally unstable N2O, which will react in a fast third step to give another water and nitrogen. So again, we check, does Hess's law apply? You'll notice N2O2 shows up on both sides of the arrows. N2O shows up on both sides of the arrow, so it cancels. On the left side, I have one hydrogen, and one hydrogen is two hydrogens. One NO and one NO is two NOs. One water and another water, two waters plus nitrogen. This result matches the original equation, so Hess's law applies. My slow step is going to be equal to some constants times the concentration of the reactants, N2O2 and H2 to the first power each. This is not the same as the experimental rate law, which would seem to indicate that this is not a possible mechanism. However, you have the species in here, N2O2. This is what is called a reactive intermediate. How you determine it? It's a reactive intermediate is as follows. You look at the original overall reaction, and you find out it's not on the reactant side, and it's also not on the product side. Therefore, it has to be something that is intermediate, something that forms above the arrow. So in this case, since you didn't put it into the reaction as a reactant, you didn't take it out as a product, you can't measure it, you have to substitute for it. How you substitute for it is by realizing the first step is an equilibrium step. By definition, that means the rate going forward is equal to the rate going backwards. Or K forward times NO is equal to K reverse times N2O2. The concentration of the intermediate is the ratio of two constants times NO squared. I can substitute that into the slow step, and I get the rate of the slow step is equal to K slow over K forward over K reverse. The values of these do not matter. Very simply, a constant times a constant divided by a constant is going to give you another constant, times NO squared times H2. So the rate of the slow step is equal to the rate of the experimental step, and this mechanism is also possible. How does a mechanism actually work? What does it tell you? What does the order of the reaction tell you about the mechanism? If I look at these two reactions, first reaction, the concentration of N2O2 squared. You see that N2O2 shows up twice in the slow step. Carbon monoxide does not show up in the rate determining step. For the second reaction, NO shows up before the rate determining step twice, and it's second order. H2 shows up in the slow step once, shows up a second time in the fast step, but it's not included. So the order of H2 is 1. Essentially, the order of a reaction, the order of each reactant rather, tells you exactly how many times that reactant is going to show up in the mechanism, either at or before the rate determining step. So mechanisms are theoretical models of how a reaction might occur. To be possible, they have to obey Hess's law, and also the slow step has to be the rate determining step, the experimental rate law. Very rarely can a mechanism be experimentally proven to be true. One simply relies on what is the best fit for the theory. And a good indication of what is the best fit is the understanding of what the order is. The order gives you an insight into how the reaction occurs. In the following video, we will look at reactions where the order is irregular, where it might be either in the denominator or fractional, and how that tells you how a more complex reaction can occur. I hope you found this video useful, and thank you for listening.